Good morning, class. Today we're going to skip ahead a little bit because I'm out today. So we're going to cover optimization. So our topic today is optimization, or applied max and min problems. Okay, so we know that extrema, possible points of extrema occur at the critical points. So that's where our derivative is either equal to 0 or it's not defined. So how can we use that fact to determine maximum and minimum values in an applied sense? Okay. So one process that we use is something called optimization for applied minimum and maximum problems. So I'm going to start off with the steps. So here are the steps for optimization. Okay, first thing you want to do is, from word problems all the way from elementary school on, is you want to identify all given quantities. So identify all given quantities and what it is you're trying to solve. So in all quantities to be determined. Sometimes it's really helpful if you make a sketch. So we'll say, if possible, make a sketch. Okay. Step 2 is we want to write a primary equation. So write a primary equation for the quantity that we want to find the max or min for. So it's for the quantity that is to be optimized. And by optimize, we mean the max or the min. So that will be your primary equation. Okay, so a lot of geometry equations, distance formula, so that sort of thing, we need to make sure that we know. Typically, your primary equation will have more than one variable. So we'll need to reduce the primary equation to one variable. And typically we will do that. We may have to use a secondary equation to do that. So a secondary equation. Then next, we want to make sure our domain. So when we get an answer, we want to make sure that that answer fits in the domain of our primary equation. So we want to determine an acceptable domain for the primary equation. Okay. We need to make sure our answer makes sense. Okay. So let's take a look. Oh, you know what? Actually, one more. Then we're going to use calculus to find max or min values. All right. So again, step 1, identify all given quantities and what it is you're supposed to find the max or min of, what's to be optimized. Primary equation is always the equation for what is to be optimized. You may or may not have to use a secondary equation to reduce the primary equation to one variable. Always keep in mind the domain of your primary equation so that if you do come up with an answer, that answer fits in that problem. And then we want to use calculus to find max or min. So we know that max or min occurs at critical points, so where the derivative is equal to 0 or not defined. Okay, let's go ahead and take a look at an example. Okay, so let's say we have, so using our process, find two positive numbers that satisfy the given requirements. Okay, so number 1, the sum of the first number squared and the second number is 27. And the product is a maximum. Okay. So here, step 1 is to identify what all the given information and then what it is we're trying to optimize. In this case, find the maximum of. So here, we're looking for the product, and we're trying to maximize the product of two numbers. So our primary equation if we have two numbers x and y, then our product is equal x times y. Now we have additional information that's given to us. So we have the sum of the first number squared and the second number is 27. But we're not trying to optimize any of that information. So that will fall under the secondary equation. So if we let x be the first number, so it's the sum of the first number squared, so that's the square root of x, x squared, plus y is equal to 27. Okay. So now we need to reduce our primary equation. So right now our primary equation has two unknowns, two variables. So we need to reduce our primary equation into one variable. and we're going to use our secondary equation to do that. So if we take our secondary equation and solve this for y, we end up with y is equal to 27 minus x squared. So we're going to take that value and substitute it in for y in the primary equation. So primary equation we can now write as a function of x. So product p of x is equal to x times y. Our y is 27 minus x squared. Distributing that, p of x is 27x minus x cubed. Okay. And now we want to take the derivative. Okay, so now that we have our primary equation in one variable, let's take the derivative. So p prime of x is 27 minus 3x squared. And we want to set that equal to 0 to find critical value. If we factor out a 3, then we're left with 9 minus x squared, which equals 0. So x is equal plus or minus 3. Now this is the part where we're going to check our domain. So the original problem said find two positive numbers that satisfy the given requirements. So at this point, we know that x is going to equal positive 3. Now we're going to take this x and solve for y. So y is equal to 27 minus 3 squared, which is 18. So our product that gives us a maximum is x times y. So that's equal to 3 times 18, which is 54. So the sum of the first number squared and the second number is 27. So it's two positive numbers. And the product is a maximum. So this value will be 54. Now here, at this point here, when we took our derivative and we have the p prime of x is 27 minus 3x squared, if you think of this parabola, we know that it's going to open down because your leading coefficient is negative. So thinking of that opening down, we know that that gives you a relative max there. So that's why we can go with that's the maximum value. Okay, so let's try example 2. All right, example 2. A farmer has 500 feet of fencing to create a rectangular pen adjacent to one of the walls of a barn. So here's a case where if you could draw a diagram, it will help you out. So a farmer has 500 feet of fencing. He wants to create a rectangular pen that's adjacent to one of the walls of a barn. What dimensions should be used to maximize the area? So what dimensions should be used? So we want to maximize the area. So our primary equation should be area. So we want to maximize the area of the pen if no fencing is needed along the barn wall. Okay. So 500 feet of fencing, rectangular pen, no fencing needed along the barn wall. So here we have some barn wall. And we have a rectangular pen. And we have 500 feet to create this. So because we're maximizing the area, so here we have an X. Actually, I'm going to call this Y. That X and this Y. So our primary equation, the area of a rectangle, is length times width. So in this case, we'll just say X times Y. So this is our primary equation. Our secondary equation will deal with the 500 feet of fencing that we're given and the perimeter that we're going to use it for. So our secondary equation is y plus x plus y equals 500. We don't need to put any fencing along the barn wall. So we have x plus 2y is equal to 500. So at some point we're going to need to take the derivative of area because that's what we're going to maximize. So here in our secondary equation we can solve for one of the variables. The easiest one looks like x is equal to 500 minus 2y. And now we can rewrite our area as a function of y. A of y is going to equal 500 minus 2y times y. So A of y is 500y minus 2y squared. Okay. So now we want to find our critical numbers. So A prime of y, 500 minus 4y, and we want to set that equal to 0. So solving for y, 500 equals 4y, we're going to get y is equal to 125. Now that we know that y is 525, and take this, substitute it in. To find x, x is equal to 500 minus 2 times 125. X is equal to 500 minus 250, so x is 250. So the dimensions of the rectangular pen to maximize the area would be to have the width of the pen 125 feet and the length 250 feet. The area, maximum area, is x times y. It would be 250 times 125. And what's 250 times 125? So that is 31,250 square feet. So that would be our maximum area. So these are the dimensions with the amount of fencing that we're given, 500 feet. We use all of that 500 feet. And these are the dimensions that would give us the largest area rectangular pen. Okay. Let's take a look at another example. Okay. So next example. Okay, so example 3. So an open box of a maximum value, so open box of maximum value, is to be made from a square piece of material. What's up? What? Go ahead. From a square piece of material that is 24 inches on a side by cutting equal squares from the corners and turning up the sides. So we want to find the dimensions of the box. All right, so this one, we got to really understand exactly what's happening here. So let's go through it again. So we have an open box. So the box has no top, and we're looking for the maximum volume. We have a square sheet of material that's 24 by 24 by 24 by 24. Now what we're going to do is on each of the corners, we're going to cut equal squares. We're going to turn it up to form the box. So the actual material is flat. We're going to cut the corners to turn it up. So what we have is a 24-inch square piece of material, and on each corner we're going to cut out so each side is 24 inches. So we're going to cut out, imagine that we cut out an equal corner, an equal piece on each of these corners. Then we take that and we're going to fold it up, each of the sides up. And you're going to end up with something like this. So here, if this whole thing is 24 and we cut out X here and we cut out X there, then what we have left here is 24 minus 2x. So now all four of your sides are going to become 24 minus 2x. Now the height, because you're folding this up, the height is going to be x. So each side of your open box will be 24 minus 2x. But your height is going to be x. All right, so in this case, we're trying to maximize the volume. So the volume, if we remember from geometry, the volume of this rectangular prism is length times width times height. So that's our primary. Our secondary equations would be the length of each of these sides. So for our secondary, our length is equal to 24 minus 2x. Our width is also equal to 24 minus 2x, but our height is just x. So our volume equation becomes 24 minus 2x times 24 minus 2x, so that's the length, that's the width, times x. And now our volume is actually in one variable. So v of x is equal to that. Now here, we need to take the derivative of this. So why don't we multiply this x through to one of these terms. So it'll be 24 minus 2x times 24x minus 2x squared. So at this point, we need to decide, do we want to use the product rule, or do we just want to multiply all of this through and then just take one big derivative in the end? So what's the easiest thing to do? Product rule or go through? Okay. So if we were to use the product rule, then v prime of x would be first 24 minus 2x times the derivative of the second. And the derivative here would be 24 minus 4x plus the second 24x minus 2x squared times the derivative of the first, which is negative 2. Okay, so what could we do now? Well, we could factor out, let's see, here of a 24, well, I wonder if we should have just multiplied it all the way through. So algebra, what can we do? Well, I have a 24 minus 2x. I have a 24x minus 2x squared. So if I factored out an x, 24 minus 2x times x, then we can pull out the 24 minus 2x. And what we would have left is this 24 minus 4x. Okay, and then we have this negative 2x because we pulled an x out here. Alright, so that's 24 minus 2x times, and over here, this would be 24 minus 6x. So that's v prime of x. And if we set that equal to 0, then we can set both of these, the zero product property, set both of these equal to 0 independently. So 24 minus 2x equals 0, and 24 minus 6x equals 0. So for this first one, you're going to get x is equal to 12. For the second one, you're going to get x is equal to 4. All right? So now we have to take a look at our domain here. Now, each of the sides, the length and the width of our box, is 24 minus 2x. If we were to let x equal 12, then you'd have lengths of 0. 24 minus 2 times 12 is 0. 24 minus 2 times 12 is 0. So this solution, x equal 12, actually does not fit in our domain. So we're going to use x is equal 4 instead. So now that we know x is equal to 4, we can find the other sides. So the length is 24 minus 2 times 4. So 24 minus 8 is 16. And then our width is also going to be 16. And our height is 4. So maximum volume would have a length of 16, a width of 16, and a height of 4. These would be our dimensions. and the volume itself, 16 times 16 times 4, based on the material that was given to us. 16 squared is 256 times 4, 1024. So our volume would be 1024 cubic inches. All right, so homework is